Hi. Oh, it's not there yet. So, just a gentle reminder that homework 2 is going to be due by Friday. So make sure that you submit on time. If you're late, you need to, the system will be closed. You have to email the TA. Okay, there will be some slight penalty for late submission. And if you want to submit your homework, you can't submit again. But if you really want to make a changes, you have to email the TA for that. Okay. Then now the thing we want to do today is to try to finish most of the thing in the in the random variable chapter. So probably we will work the normal discipline out, and then probably what's left Excel. So probably you will be done with this chapter. Okay, and I will probably release the homework like after next class. Okay, after the weekend, probably after next class, we cover everything up. Then there will be assignment will be released. So what we're going to do today, as I said, is we will cover most of this topic. Probably next class we'll finish this up, and the next assignment will be released probably next week. Okay. Again, you're given 10 days to finish your assignment. Okay. So again, the assignment is intended to make you familiarize with the material and the material that I think that is important. Okay. It will be very similar to the example that we have covered in the class. So if you know how to do the examples, then you should be able to do the assignment. Shouldn't be an issue. So let's quickly review what we have been done, and then we will continue our journey on this. Okay. So random variable, okay, as you might be expecting, will be a way that to put in numbers on the outcomes of the random experiment, right? Probably you would remember that. And you should also remember, depend on what kind of number you can put in, would distinguish what we call the discrete or a continuous random variable. If you put natural numbers, that will be a discrete version. If you put decimum numbers or real numbers, that become a continuous. Okay. So we learned that to describe a discrete random variable, there are two ways. Either you've got the big P, which essentially said if you have a number, give me, I give you the probability, right? And there's another one, you got F will be, you give me the number, I give you the probability that less than or equal to that number. Okay, so there were two ways, and they are the same way. Okay, just you can convert from one to the other. And after that, we learn how to use the random variable, because they're numbers, where naturally you can think about mean, variance, and mode, and kurtosis, skewness, and all these are meaningful because probability in classical sense is defined Norman frequency. So it means that if we actually repeating the experiment, random experiment, many times, and you observe many outcomes, and the outcomes would appear in relative ratio according to probability, right? So that's why mean and variance will be a weighted mean, right? Taking the probability P as the as a weight. Okay. And we have same idea. We have the variance and so on and so forth. Okay. And just do note that we focus on the idea of having a single number, okay, to represent the outcome of the random experiment, but you can actually consider two or more numbers, and there's no problem in terms of theory But if you consider math, calculate expectation, the two numbers may be related, okay? And in this class, we focus on the case that independent, right? When focus independent, then basically you can consider them separately, right? So that means that we don't really need to go into the details, right? When the sum will be same, some of the variance of sum will be some of the variance, okay? So that makes things simple, okay? So that is what we will be doing for most of our case, okay? And we call that we also did a discussion on a common discrete random variables, right? We have polynomial, binomial, Poisson, and hypergeometric. Just to remind you that when we use binomial is something that outcome can be divided into success or failure, right? There can be many outcomes, but when we talk about random variable, then you just say either you success or failure. And for Poisson, it's just asking how many events that actually occur within a period of time, or how many customers coming within a period of time. So it's a very useful technique. And hypergeometric and the binomial are very similar in the sense that they're just drawing things from an urn, and binomial is being once you draw it, put it back, and hypergeometric you don't put it back. So it is especially useful when we talk about quality control or audit. Okay, so that is how this being done, and how it actually applies to audit. Later you will see when we do topic 5 and 6, hypothesis testing and over. These will be the case where you would know how they being applied, but we don't cover in the class. But you can see the similar idea can be done with respect to hypergeometric. Okay, in this class, after this topic, we just focus on binomial. Okay, binomial, the thing we cover, Poisson hypergeometric will be gone. So we will not talk about Poisson hypergeometric. So basically, it's binomial. And after that, we go to talk about the continuous random variable, okay, where we only define f, okay, and probably you ask yourself, what is the big P there, right? You may ask why we don't define big P, because it's meaningless to define, because big P is always 0. Because continuous random variable, you are asking the value can be any value in between some interval, but continuous. There's a many infinite many of them. Then if there's a particular value, right? But probability that equal to that value will be 0, always 0. I mean, in general, right? So that's why we don't talk about P, but instead talk about F. F is asking an interval, right? Asking what is the probability that less than certain value. And when you ask the meaningful value, then this F will be meaningful, right? And just to here we see integration, right? And we see this thing, right? And probably you can ignore, right? You just need to know for f actually coming from a small f, okay? Small f in integration means the area under the curve, right? Area under the curve will be the probability, right? Just to we emphasize again what actually we are talking about is when we have continuous random variable and we look at the density function, the small f, and the small f, and what is this small f tell us is, suppose I have a number A and number B, okay? I want to know the following: probability X is between A and B, whether you have equal sign doesn't really matter because we know the equality don't change anything. So that will be saying this is the coming from this area, okay? This area under A and B is this, is like area under F between A and B, okay, is what we want to find. And this is also equal to this, right? If you talk about big F, okay, something like this. And you also can look at between A and B, okay? Look at the F of B, and this is F of A, okay? And the difference is also the same thing. This is something you probably need to know, and I hope today we will repeat this enough so that it goes into your mind. The reason of this is very simple. Geometry problem in the kindergarten, right? The red area will be same as, let me close it down here to make it simpler. The red area will be same as you take the orange area, okay? And you also have the green area, okay? And you subtract green from orange, then we'll give you the red, right? So the green will be this guy, right? And the orange will be this guy, right? So green minus orange give you the red, okay? So that is the thing that we'll do it today again. Don't worry, we'll be doing this today, so you would definitely know, okay? We talk about bell curve, that will be something we'll keep doing this, okay? So don't worry, we'll be doing this again, okay? So I guess that's okay. And just to here we talk about expectation and variance for a continuous random variable, and indeed you don't need to worry too much about the notation. We have integration of this, but that is how you calculate if you really have to calculate, right? But the idea is same as discrete. The idea is you just repeat this experiment many times. You record all the x, you calculate the average, the same, okay? Will be give you the expectation, and the variance will be the same idea if you keep doing the same thing, okay? And that would be the idea of this. And then actual calculation will be like this. And the idea of expectation is actually no different from the discrete version, okay? Let me convince you this is the case. So if you recall how we do expectation in discrete sense is you have x, you have p of x, right? And then say you have a value here, value here, value here, right? And what we're going to do, right? The height is p of x, right? So expectation is given by summation x times px, right? So basically it's just what this value is multiply the height, right? It's the bar graph, right? It's what is the number here, you multiply by the height, okay? That is what do we mean by expectation in the sense of a bar chart. I don't know, the probability function, you draw a graph, okay? So actually this actually can be translated into f, okay? Consider the same idea, we have f here, okay? And f is something like this, I guess, okay? Something like this, okay? So with the same idea, if we are thinking is we draw a bar chart here again, okay? The same idea. If I have the height is called f of x, okay? And the difference is called dx, okay? And the mean will be expectation, will be similar. It's just sum of all the fx okay, times d of x, okay, and you just add them up, okay, okay. So, and you can also the location here x dot, sorry, x dot dx. So this will be something like this, okay, x dot dx, okay, and you will be replacing this by integration, okay. So that is why you have this in where is this, okay, why you have this in the slides, okay. That is actually what this is about, okay. And but I probably you don't really need to worry about the notation, but this is what we have, okay. Now the goal of today is to try to finish all, if not most of them. So we I think we have covered uniform already last class, okay, and we cover exponential also. I mean, we will review it, okay, and then the goal today we will cover normal, okay, the bell curve, the famous bell curve. This is the main focus of today, okay, and then for the rest, okay, we will just briefly touch it. The reason is being that they will be introduced again in the rest of our course, but I just want to mention it right now. We'll briefly tell you what they are, and when you see it, you will not be surprised, okay. So mainly what we will learn is the normal today, and we just let us briefly review what these two are, okay. And just to remind you what is uniform. Uniform is given a interval, any value within that interval will have the same probability. And exponential, what we'll be doing is asking the question of in a time period, okay. And we do in the Poisson is saying we cut this interval into very small intervals, sub-intervals, right? And we said each interval as an event with probability p, right? And we cut it into n pieces, right? We have the idea is with n have very large, right? And p is small, but it's not so small such that n and p is equal to lambda. Okay, it's still a non-zero. Okay, it's so small, but np is still there is still a positive thing happening inside. Okay, and in that case, it's Poisson. Okay, and Poisson tells us how many. It's a random variable that record how many events happen in that period in this from 0 to t, right? So it's about number of events. Okay, exponential is asking the question of what is the time that first event comes out. Okay, it's a time. So it's a time. That's why random variable is a time that comes out is bigger than equal to 0. It can happen at a 0 second, but it will go from 0 to infinity. Okay, so it's modeling time. So why we still cover this? The reason is bell curve, although it's very commonly used and doesn't really fit very well for the time. Right. Later you learn bell curve will be applying to many purposes, but it is not so good to talk about time because time do not have negative. Right. You model the time normal. Later you see bell curve, probably you know is going from negative infinity to positive infinity. Right. Any negative number will be included. And we still need to talk about uniform is because right you don't have some you have some idea that actually is not negative, right? So that is better, right? And uniform also serves that purpose, right? If we know the random variable actually range from some positive numbers, right? And probably it's not very good to put a normal, right? But of course, later actually you will see if although normal allow negative number, okay, but the bell curve actually most of them would fall in 3 standard deviation. Later talk about the empirical rule, right? Today is talk about the 3SD rule. It's like 99%. We actually will within the 3SD. Okay. So using normal, it'll be fine if the variance is not very large. Okay. After the 3SD from the mean is still positive, so you should be safe. Okay. But for the time, exponential will have a nice property because we talk about one thing is important is if you believe the process is memoryless, then it will be exponential the best thing you can do. And actually, as I told last time, is when you talking about a random variable that actually has memoryless property, the only thing you can do is exponential. Okay, you cannot do other way around. Okay, so if you actually the process is memoryless, then exponential only way you can model. You cannot do other things. Okay, and so let's review what we have done. Okay, and uniform, we're talking about things equally possible between A and B, and the only thing is like we have the F will be the same for any value there. And just remember the denominator comes from the fact that the area under the curve must be 1. Just quickly to remind you why this is the case is this is A and B here, right? And the height is flat because the height is flat is because the area under the curve represent the probability, right? So every point the same, right? So it must be flat, right, for the F. Okay, and we also know that the area under the curve between A and B, right? This area is the probability that the random variable will be between A and B, right? This is the probability that X is between B and A, right? We have talked about that. Okay, and we know this must be 1. The reason is being that I told you that it must be A and B, right? So it must be 1 because coming from the axiom 2 of probability, right? It's the sample space, right? This is a sample space, right? And that's why this a rectangle is the area. The area, the base is B minus A, right? So the height must be 1 over B minus A. Okay, so I hope this will remind you why we have the F, right? And of course, no one would bother with the F, right? Because you don't do integration. But you can easily check using the math in your high school to show you that if I have a particular value of X here, okay, I want to calculate this area, the function is given by this one. Okay, actually, you don't need high school math, but I think primary school math would do, right? Because the base is X minus A, right? The height is B over A, so this is what we have, right? Just the base is X minus A, the height is 1 over B minus A, so you multiply, right? So this is just a primary school math. Okay, again, I told you we don't need to know, you don't need to remember how we derive it, but I just telling you that how it can be derived and just the process that you know how things comes about. Okay, it's not necessary to remember the thing. You have the feeling of this, and when later stage you learn much more deeper probability of statistics, then you know how they are derived. Okay, you don't need to remember it, right? You just need to know what they are. Okay, and just to remind you that when we use it is we don't know which one is more likely. Usually it's a starting point of building the model, right? If you believe learning, you believe Bayesian updating, you believe Bayes theorem, you can start with the uniform. And although we don't talk about this in our class, you can, based on the data, you keep learning the process, you keep updating, and end up with another distribution, and then keep updating, you get the right one, right? That is actually how science or how engineering model works, right? You assume some assumption, and then the data will tell you what is the appropriate one, right? That's how the training or all that works out, right? So then you start from somewhere. This is the good thing to start if you have no idea what is more likely, what is less likely, right? And now the next thing is just very simple, just where we remind you the mean is in the middle, right? Because we have things from A to B, right? The midpoint is A plus B over 2, right? Because anything is possible, right? The mean is the middle, right? Because of the idea that mean is in terms of distance is same for the left and to the right, right? We learned that that was the meaning of the mean, right? So that's why exactly the middle point is exactly equal distance from each point is there, right? And the variance is in a sense that if you have A and B is bigger, the variance is larger, which is normal, and the denominator 12 is probably I said last class is I don't have a good idea why this is 12, but this math tells you this 12, but I mean there's no, I mean you look at the proof, you will see why it's 12, but I don't have good intuition why this is 12, okay? But it happens to be 12, okay? So lastly, let's review the exponential, then we go normal, okay? And exponential, as I said, it just you consider Poisson with mean lambda, okay, asking the what is the time until the first success, okay? And important point here, as I mentioned, is memoryless, okay? Just to remind you what is the memoryless, it's saying that, okay, if you say you wait, you expect that the next, say, suppose you go to have a dinner appointment with your friend, and the friend did not come in the scheduled time, then you may form a probability that he or she is coming. You think that maybe with a probability of half, he or she is coming in the next half an hour, okay? And this judgment remain the same no matter how long you wait. So you wait 10 minutes, you still believe that he or she arrived in the next half an hour is half, okay? And after you wait half an hour, you still believe so. And you wait for an hour, you still have this same belief, okay? So the probability you assign is regardless of how long you have been waiting, it's follow the exponential, okay? And if you probably remember, if you ever study physics in high school, right, this is exactly what happened for, it's a good thing you try to model nuclear reaction, right? That's actually the radioactive thing is actually following this, right? And also you would think that this also fit a lot of business application in the sense that how long that some customer is coming, right? Usually is independent. If you believe Poisson, if Poisson is the appropriate assumption, then exponential will be appropriate as well, right? Because this is basically a Poisson thing, but you talk about time instead of customer arrive, number of people arrive, right? And for exponential, the why it comes from this name is basically the f looks like this guy, okay? As you will see in the next slide, this is what it looks like, right? So it's x is f is exponential decay, okay? So if you try to remember if this is the mean, okay, this is the mean, okay? Mean is actually 1 over lambda, which we explain later. Is inverse related to the Poisson. Poisson's mean is lambda, the time is 1 over lambda. We explain that later, but you will notice that the median, because this guy is actually skewed to the left. Actually, the median is way much earlier. Okay, so although the means here, but most of them actually arrive here. Okay, and the main thing is, of course, we don't care about small f, but the big F. Okay, big F is this function. Okay, this is something probably you'll be using for your assignment, right? And this will be also we show the example. This is the important number, right? And now we try to explain why we have 1 over lambda in this particular case, right? Just to give example to see why this is true. Consider the case where you have a Poisson, right? Process Poisson thing over an hour, okay? And we say lambda is 2, okay? That means that on average, within an hour, you have 2 success, right? And that means that actually you expect, that means that every 30 minutes you have success, okay? Because you have 2 success in an hour, so 1 over 2 hour, you should have 1 success, right? 1 over 2 hours, 30 minutes. So you wait 30 minutes, you have 1 success, right? So that's why the mean is 1 over lambda, right? And by this example, you can immediately see that why we only talk about the first success, right? Because of memory loss, right? The first success is same as second success and the first success and the fourth success, right? So there's no need to have separate thing just because once you have success, you restart the whole thing, right? There's no memory. The history doesn't really matter. Doesn't really how many arrival have been happened before. When you start from now, it's now. Okay, you just forget the past, basically, right? Memory means past. The history has no meaning, right? You're very forgetful, okay, when you talk about exponential. Okay, I hope this is clear what we have so far, exponential. Now we talk about normal. Okay, normal is I think we stopped somewhere here, right? Last time. Am I right? Okay. The bell curve, okay. And this is the thing that is the most useful one, okay. And as we probably you know from your high school that our bell curve is particularly suitable for looking at IQ, looking at the weight, looking at the height. The reason is being that IQ, weight, and height are determined by many factors, right? IQ determined by your genes, your parents' gene, your parents' gene, so on and so forth, and also what you eat, right? What the temperature, what the environment around you, right? There is many factors adds up. Same as weight and height, all the things actually determine that, okay? And that's not a coincidence. Actually, this comes from the fact that we have in statistics what we call the central limit theorem. Actually, we'll cover, I think by the end of this month, you should know this theorem, which essentially said, in loosely speaking, is when when a measurement or a random variable actually comes from average of other independent random variable, right, and end up in the bell curve. Okay, let me repeat the statement. Is when we talk about the mean of any type of random variable, okay, end up in a normal. Okay, because you can imagine IQ is the mean of average effect of everything, right? And that's actually why we study bell curve in our class. It's so important because, right, because we care about the sample mean, right? We are drawing observation from population, right? And indeed, the central limit apply, the central mean actually will follow a normal. And actually, it is the foundation for everything we do for the rest of the course. All right, from next week, we'll talk about sampling distribution, hypothesis testing, estimation, regression ANOVA, everything rely on bell curve. So that's why please pay attention to what we're doing today, as if you don't know what we are doing today, then you will be confused for the rest of the course. Okay, the bell. So that's why it's important. I mean, we'll cover this, so don't worry. We just give you idea that why many things are bell curve. Because if things are, what you observe is coming from average result of many factors, and these factors are more or less independent, and then you will have a normal. Okay, so but we will be more precise later, but just we keep it loosely because we can only define when we know what we're talking about. But and the bell here, the F will looks like this shape, and then probably some of you might ask, do we need to remember all this? No. Okay, and if you ask me to write down this expression, okay, if you stop me in the hallway, do I know that? No, I don't. I mean, I have to check it out. Okay, and of course, if I'm teaching, I know, but if not teaching, it's not. Then, but you need to see what is the main thing in this formula. Is one thing is probably you don't need to see this, but you can actually see the bell curve coming from this, and there's several observations here. First is the middle is mu. Okay, it's the peak is the mu. Probably you may be able to see it because it's negative to a square, right? So then the biggest number up here when x equal to mu, right? So from this you can see the highest point, and because of square, right? So that means it's symmetric about mu, right? So the first thing is from this peak at mu. The second thing is symmetric about mu, right? That's two things, right? And third probably don't see, but it's like exponential drop here, right? Because E, then it's just like this kind of style, okay? And it's like the bell is a bell, right? Looking from this, because it's like exponential idea, right? But you have square, so it looks like that. That's kind of bell, and and because of this, right? And it's symmetric peak up there. Also, the skewness is also zero, right? But anyway. And the first thing is you can see from this is the sigma square, okay? The sigma actually affecting the shape, right? Because look at sigma square, increase the sigma square, right? The denominator will get bigger, right? So it's actually getting flatter, right? So is that make it flat? Okay, so we can make flat. Okay, if you change the mu, we just move the location, right? So the two things is mu is moving the location, sigma is making thin or fat, right? Okay, or tall or short, if you like, because thin and fat and tall and short are related, right? Because the area under the curve F is always 1, right? So this area is always 1. So if you make it taller, then it must be thinner, right? At the tails, okay? So but that it can be obtained from this graph, right? So first look at the blue, compare blue and the green, okay? The only difference of this is just the mu, right? So you can see the graph is just like if you change the mu, okay? You just shift left and right, okay? You're just moving back and forth, okay? And if you change the sigma, compare the color, okay? Compare these two, okay? You just basically shift this up and down, right? You just if you increase the sigma, you just use the hammer to hit the tip, and then you will just compress into the lower one, the red one, okay? Because the total area is 1. Okay, so that is the mu and sigma, and you probably don't realize this is one important thing here is mean is given by the mu, right? And actually the variance is given by the sigma square. And that is actually why we choose these two parameters, because exactly they are capturing the mean and variance, right? And you do notice that the mean and variance are captured by two parameters and they're independent. And that is very special case, right? Because remember what you learned from your binomial, right? Mean and variance are related. Poisson, mean and variance are the same, right? And uniform, also mean and variance are related to A and B, right? And exponential, they are related to lambda, right? But for the normal, they're independent. Okay, they're controlled by two separate parameters. Okay, so that is one important thing here. And that is actually interesting thing indeed. Okay, and first with a shorthand notation, we have x. If a normal with mean, mu, and sigma square, we write x as neg and n. So that's notation we'll be using for our class. So just let you know. And first thing is you can see because of the graph, actually you would expect this is true. If x is a normal with mean, mu, sigma square, you multiply by a constant and plus a constant is still a bell. Okay, so this is a very important idea of the bell curve. Is that if a bell, okay, if you add some number there, okay, you just move it by b, right? And if you have this, right, this at b, right? If you multiply by a, okay, turn out that you just everything multiply by a, okay, you just spread out more, maybe not that tall to be okay, just spread out more, okay, and they still a bell curve, okay. So this is does not hold for many cases, right? Suppose exponential, you add a number there, it's no longer exponential, right? Because exponential must be between 0 for infinity. You add something, it's no longer exponential, okay. So same as binomial, you add something, it's no longer binomial, okay. But strangely speaking, normal you add multiply is still same as normal. So this is very important, okay, and very useful thing, okay. So probably you ask how from here you get to this guy, okay. This is very simple, right? You have see this already actually. If ax plus b is just a expected x plus b, okay, and this guy is just mu, okay, and that's why you have this, right? Because it's a mean, right? And we have a variance of ax plus b, right? Will be just a square variance x, right? This is just sigma square. So this comes explain this guy, okay? So this is the idea, okay? Just if you adding something or multiply something to a random variable that doesn't change the shape, okay? And as I emphasize again, this only apply to bell, okay? If not bell, you do not have this, okay? It's very important idea. And you may ask why this is important, okay? The reason is that this would simplify a lot of calculation, okay? And why we need that? Is that okay for this one? Okay. And the main reason we need that is because remember the f of x of the normal is a very complicated integration of the thing. And actually, if know math, you know this is no closed form solution. Okay, that means that you cannot use pencil to calculate. You must use computer, right? And very often we actually need this guy, right? I mean, although normal is very simple, we can have mu and sigma, then we can calculate mean and variance, right? But the probability, we require computer to calculate, right? And that make things not so easy. Okay. So the key here is because of this transformation, okay, we can always do the following transformation. Okay, if a x is following normal mu sigma square, we can always do this to make this as mean zero variance 1. Okay, and okay, if you don't believe, you can just say use the last expression. A is just 1 over sigma, okay, and B is just negative mu over sigma. Okay, you put that to the previous page, that is what you get. Can you see that? Look at your slide, check it out whether I'm right or wrong. Okay, okay, if you don't want to check, let me show you. Ax plus b is normal, a mu plus b, and a square sigma square. Okay, so what we have now is a is 1 over sigma. Okay, a mu plus b is 1 over sigma mu minus mu over sigma, which is 0. Okay, and we have a square sigma square is 1 over sigma square times sigma square is 1. Okay, so the standardization, what we're doing is, if we have a random variable, okay, if you consider the transformation minus mu over sigma, you become a normal CO1. Okay, so what actually we are doing is, you have some normal, okay, and we can always transform this to a z, okay, where this is mu. Okay, we can always, maybe I just don't use this, I change the color. Okay, we have mu here, okay, and we have variance equal to sigma square. Okay, and we always can transform it to mean 0, variance equal to 1. Okay, in this case not equal to 1, but you can always transform this to this guy, and probably you want to ask why we are doing this. Okay, why we want to transform from x to z. Okay, why we want to do this operation here. Okay, why I want to do this operation. The reason is being that, as I said, we want to calculate this guy, say, okay, there's some number a here. Okay, we want to calculate this probability. Okay, so you want to calculate probability that x less than or equal to a. Okay, and remember, there's no hand calculation method to calculate this guy, right? You need to calculate integration, right, in computer. Okay, and in the old days, this is not very convenient, right? Because you do not computer, right? You have to do integration. Is very complicated process. If everyone ever know how to do integration by hand, right? And the important thing is, right, when you need to do it, you need to have usually you do a table, right? This is actually f of x, right? So actually in the old days, you probably need to have this, right? X, f of x, a table, right? For different values, say -3, -2.9, -2.8, so on and so forth, right? Your table. And whenever you need to pick up what's the A there, look at the table. Oh, A is here. Oh, this is a number, right? And the problem of this is normal have two parameters, lambda and sigma square, right? That means that if you really want to have a table, okay, do the pre-calculation, you need to have a table for each possible lambda and sigma square, right? That can be a very complicated thing, right? Because any combination you have a table, right? You have table for mu equal to 0, sigma equal to 1, mu equal to 0, sigma equal to 2. Everything you need to have a table, right? And it's not possible to have such a table. Then you'll be very thick, right? The good thing is you can always transform this to here. Okay, transform this to this guy here. The transformation is just A minus mu over sigma. Okay. Once you do this, this area will be same as this area. Okay. It means that we don't need many tables. We just need only one table. Okay. We only need to transform x less than a, okay, to the question of the same as probability that z is less than a minus mu over sigma. Okay, so this transformation would help us is we need a many table. We just need one table, and that table is called z table, and we'll talk about this after the break. Okay, so the transformation tells us we don't really need to worry about x has different mu, different sigma. We can do this transformation. Okay, when we try to ask the probability less than a for x, we can transform this to z, which is we ask what is the probability less than a minus mu over sigma. Okay, in that case, our life will be easy. Okay, this is called standardized normal. Okay, and that's we will call z, and then we will be using it. We will talk about how to look at the tables after the break. Okay. I guess you may have many questions, and I just have a break, and we resume at 12:30. In the meantime, I just go around to see if you have a question. So I guess I explained to you why we're doing this is because of we don't want to check, we can't really check the table, right? Because there are many tables to check. But when you transform a normal to a standard normal, we can create a table and check. There's only one single table need to prepare, right? Otherwise, we have to rely on computer every time, okay? So let's see the example, then you will understand what we are doing. Okay. As I said, we will have a table. Okay. And this table, right? Z, remember what Z? Z is normal 0, 1. Okay. And what we are doing is we will have a Z table. The Z table actually gives us what is f of Z. Okay. Or in the other words, you give us, if you give me a Z, this table will give you this number. Okay. That is the Z table tell us. And the thing you need to think about is the Z table. If you look at the internet, there are two versions. Okay. And one version is they give you only negative number. Okay. The other version is they only give you positive number. Okay. So two versions. One is negative number. Version 2, positive number. Okay. And you may ask why you have these two versions. The reason is because this is symmetric. Okay. If I have the negative version, okay, I can also have the positive version as well, because this, okay, you flip it, okay, it's the same. So suppose it's -2, okay, look at the 2, you can calculate this value, the same area, okay, and you 1 minus this area, right, will be this area, right? So that's why you only need to have the table that either only cover the negative or opt for the positive. Okay, because one is the negative, you just flip it over and subtract will give you the positive value. Is that clear? That is what actually means here. Okay, don't worry. Let me look at the table from the internet. You will see what do I mean by this. Okay, so let me randomly look at the Z table. Okay, on the web. Okay, in this one, okay, actually maybe it's a good one, good table. Okay, and let me clean it. Okay, clean out the drawing. Okay, here this one is give me the negative value. Okay, so that's why you give through from 0 to negative 3.4 to 0, and this one gives me the positive value. Okay, and they're the same. Okay, and actually, right, if you do Excel, you don't need to distinguish because Excel gives you the answer directly, right? But if you go to the test where you can't use Excel, okay, you can bring this table in or bring this table in, also the same. Okay, but you can bring the both because there's no limit number of pages you can bring. So you can bring both, but or you can bring one of them the same thing. Okay, I will illustrate how to use this table very soon, but this is the two tables that you can use, but you will see that they're the same thing. Okay, so let us go to try to check this out. Okay, this one is asking a Z table. Okay, the first question is Z is less than 1.4. So very simple, just this question, right? 0 is here, we have Z, we have a bell here, okay, and we have 1.4 here. Okay, the question asks you this guy. Okay, and immediately you will see the easiest thing to do is to check the Z table that gives positive value, right? Because this is exactly the positive value one. But of course, I will show you. You can also do the negative 1.4. Okay, you check out the blue value, and this blue value will be the same as this blue value, and you subtract from 1, you get the same answer. Okay, let me do the both. Let me do the red thing first, do the positive value. Okay. So let's see the graph here. Okay, we do this one, the red value is 1.4. So 1.4, look at this one. Okay, this is the positive one. Okay, and the value we have is 1.4 is exactly this guy. I'm not sure you can see it clearly, but this is exactly 1.4. And you may ask, what are the column this, right? You first read you show the first column, look at where the first number is, 1.4, and then you just try to add this 1.4, this 1.41, this 1.42, so on and so forth. And you first look at the first column, right? Because this is the first one you do. But look, just like the dictionary, right? Look at the first letter and the second letter, and look at the first letter first. 1.4 exactly, this is 1. Okay, 0.9192. Okay, and I tell you how you can do the same using the negative value. Okay, in case you only have one table. So look at this the same, but look at negative 1.4, and that gives you the blue area is this guy. Okay, 0.808. Okay, and 1 minus 0.808. Okay, it will be the same as what we have seen, right? So either use the red or the blue, the same. Of course, in exam, you don't want to waste time, just bring 2. Okay, and probably you ask which table you want to download. So don't worry. Next class, we'll do Excel. You can create your own table. Okay, you can create your own table. We don't really, I mean, of course, you can download, pin out the table here, but I will tell you how to create your own table. You can do whatever you like. Okay, all this entry, you can use Excel quickly, you can create. Okay, you can create actually less than 10 seconds if you know. Okay? It's very fast. I actually say exactly 10 seconds, you can create one table. So you can just do the way you like. Okay, but if you hurry, you can just pick up any C table, it's fine. Okay, and a textbook will give you the set table. You look at the textbook or any other Wikipedia or anywhere website, you have the Z table. Okay. Now let me do a several more example because we will be using it. Okay. Why I spend so much time on this is because we'll be, as I said, we'll be using this for the rest of our course. Okay. So we'll be doing this repeatedly. Okay. Of course, when you do assignment, probably you consult Excel rather than the set table. But in the exam, we need to rely on this. So we still need to use the low-tech thing. Okay. And here is less than 1.6. So let's draw a diagram here. Okay. Remember, normal has mean 0 here. Okay, that is here. And 1.6 negative is here. Okay. So the question is asking this area. Okay. The smart thing to do is look at the negative table. Of course, you can look at positive as well, but positive, what you do, you will be actually doing this, right? 1.6, and you'll be doing the red area, but you should subtract 1 from the next area, then we give you the orange, but the orange and the green are the same. Okay, so you do one way or the other. But let's do the green thing first, and now I will show you the red. You will see same as the orange. Okay, because 1 minus red is orange. Okay, is that okay? Is that a question? Okay, so let's find the first thing. We look at negative 1.6 should get you this number. Okay, 0.056548. So let's see whether we get this number. Okay, now let's look at negative 1.6. Okay, and so we're looking at the negative, so negative entry will be the easiest thing. Okay, negative 1.6. Okay, we only need to check the first column, same idea. Negative 1.6 is exactly here. Okay, this guy. Don't know whether you can see clearly from the back. If you are at the back of this, the class, then this is the number 0.8548. Okay. Don't worry, if you do Excel, then immediately you come out this quickly. Okay, but we look at table, then this is what it is. Okay. Okay. And remember we said we can also do the red one, use the positive one. Okay. Positive one is this guy. We have to look at the area, then subtract from 1. So 1.6 is this guy. It's 0.9452. And 1 minus 0.9452, get the number you get, right? So that is the answer. Okay? Is that clear what we are doing? Okay? The next one will be actually not that difficult. If that's okay, then we erase the drawing. In case I erase things too quickly, you can check back the video I upload on the web, then you can just draw again. I mean, everything is uploaded, so that's why if I accidentally go too fast, you can just check it back. Or of course, you can ask me, that would be easiest. But I'm not sure every time I can produce whatever I draw, because every time is a little bit different when I teach. But anyway, so this is Z, right? And 0 is here, and this is the graph, okay? And what we want, the question asked is negative 1.6 and 0.4, right? So that is negative 1.6 and 1.4 here, okay? And this area they want, okay? And this area they want is somewhere in the middle, right? But from the first question and the second question, actually you pretty much know the answer. The reason is again a kindergarten math, okay? The first one you have done is the green one already, okay? The green one is this number, okay? 0.9192, right? And you also have the second one, less than 1.6, the blue one, okay? It's this guy, okay? You have that already, okay? And this kindergarten again, green minus blue is red, right? Or if you like blue plus red is green, right? So then you know how to calculate, okay? And we will be using it all the time. So just make sure that you're happy with that. But don't worry, if you're not happy right now, you'll be happy soon because we'll keep doing this. Okay? So is that okay? If okay, then we go one more step. Okay, this is only looking at the Z, and this is only the last step we're doing because we usually have the X, it's normal, and then we transform to Z. Okay, so let us give exactly what we need to do right now. Okay, but before we do that, I want to talk about this special rule. Okay, this rule is very important even to management, and some of you have reading the management notes during the break, but that is actually they are doing. It's called the empirical rule or the 3 sigma rule or 68, 95, 99 rule. If you look at Wikipedia, you know the 3 names mean the same thing, right? Probably you guys are too young, but 10 to 15 years ago, there's a very famous a lot of book called Six Sigma or the Sigma, and then at that time Sigma, right? It's a very famous term. And what does that mean in our context here is the following, okay? So we will look at the table, okay? And you can show the following thing, but let me open a white space, okay? What happened is from the Z table, you can verify using the method we just did, okay? Z here, you have a bell curve here, okay? This is 0 is here, okay? And you can essentially check the following. If this is 1, negative 1, this area is 0.68 or 68%. Okay. And if you have 2 here, negative 2 here, this area is 0.95. Okay, and you have 3 here, negative 3 here. This area is 0.997, right? Is it 997? Am I right? 0.99 is fine. 0.99. Okay. So it means that if things follow normal, which you applied IQ or whatever, more or less like 70% is within the first SD, 95% within 2 SD, 99% between 3 SD, right? 3 standard deviation. Okay. And what does that mean? It's a shortcut empirical rule. It's a rule of thumb in the sense that you know how well you're doing without going to the Z table, right? Because this is the number that you will be in your mind. Okay. So what is the application of this? Okay. Actually, you can apply it all the time. I think now is the midterm peak season for many classes. Luckily, we don't have midterm. I mean, hopefully you like the way we're doing. I mean, if you like midterm, let me know. I mean, we can make it this year, but if not, we can also make it next year. All right. But I guess midterm, I don't think we need a midterm, but if you know, let me know. But so what is it important? Because after midterm, right? Usually you will be given your score, right? Then you will ask how well you're doing, right? But how can you know how well you're doing? And usually teacher give you 2 summary statistics, right? Give you the mean, give you the SD, right? Or give you the SD, right? Just not the sigma S, right? Say, suppose the mean of the exam, midterm exam is 18 point, SD is 5, okay? And so if you have a score of 90, okay, then you ask yourself how well you're doing, okay? And immediately actually you know, okay, based on the calculate, based on if you assume it's normal, right, which is usually the case, you are 2 SD above the mean, right? Because 80 minus 90 minus 80 over 5, right? So your Z score is actually 2, right? Which means that you are actually very good, right? Because 95% are within 2 SD, right? Actually, you are basically top of the class. So basically, you should get an A, right? If you continue this performance in your final, right? And if you actually got a, say, your score is like 75, okay? Just 1 SD below, okay? You may think it's still okay, but you look at the data, right? Actually, a lot of people are higher than you, although you just 1 SD off, right? Maybe you're expecting a B or, I mean, B plus or B, right? Or even B minus, right? Even though it's just slightly 1 SD below, but 1 SD is actually a big thing, right? So you see 2 SD already, you are top of the class, right? And if you got 70, then probably you are failing if you continue this thing, right? So that is the one thing that normal is being used, right? So look at the SD, 2 SD or 3 SD is already enough. A 2 SD is already enough with 95%, okay? 1 SD is already 1 SD looks like a trivial thing, but indeed 70% is within 1 SD, right? If you're in the fringe of 1 SD, then actually you're not doing very well. Although it seems like you just 1 SD behind, but actually not that good. Okay, if you are actually 185, again, right? Actually, although you just 1 SD above the mean, actually you're doing pretty well, right? Because 70% are actually within 1 SD, right? You are the fringe of 1 SD, actually doing pretty good. Okay. I get this pretty much I want to say, and this is a rule of thumb. And if you learn statistics, so actually you don't need to remember this rule, right? But I just put it there because this is sometime when you look at management class, they will mention that. Okay? Just 2 SD is sufficient for most purpose. Okay. And the next thing I want to talk about is what we call inverse normal. Okay. Inverse normal is just opposite the case we have seen. Let me go back to here to explain. Okay. So what we have is we ask the question of the following. Okay, we have a Z0 here. Okay, and we are given A, right? And then the question we have been talking about is Z less than A is what? Okay, we ask this area and we know how to do it, right? This is the Z table tell us, right? But very often we want to ask another question that's reverse is we have a 0 here again. The question is I have area here, okay, called alpha. I want to know what is this number. So the question is Z less than is alpha. What's this guy? Okay. And and very often the notation, I just follow the book. Usually the book would, instead of asking this, they ask this is alpha. Okay. So they would ask alpha and they call that Z alpha. Okay. And why they do this, I don't know. This is how the book would say. And of course, this would mean negative Z alpha. Okay. This is negative Z alpha. Okay. So this is the notation used in the book. So that's why I follow. But I don't know why they do that, but the same thing, the symmetry. Right? So you will see later why we want to do that. Okay. We just do the calculation and we use this thing in the rest of our course. But this is the thing we do calculate. It's the inverse normal we call. But we will just use the same table. So don't worry. There's nothing new, but just reverse search. Okay. So the example is the following. Okay. The question we're asking here is, I want to know the Z such that, okay, I want to know the following. I give you this table, okay, 0 to the Z, okay. I want to know the value of Z such that the area to the left is 0.95, okay. And you will immediately see it shouldn't be on the left-hand side. It must be on the right-hand side. The reason is because 0 is the middle point, it's a median, right? Left of 0 is 0.5, right? So it must be somewhere here, right? Because here it's only just 0.5, right? So you have to move beyond 0.5, right? To get this is 0.95. So what the question here is, if this is 0.95, what is this guy? Okay, so that's the question. So reverse, we have fun, right? Before we give you the Z, we want to find the probability, but we just reverse. Okay. So we know this is going to be positive, right? The easiest thing is go to the positive Z table. Okay. Of course, you can do a negative one and just reverse, but we do both. Okay. So what we do is look at the Z table, look at 0.95, or use the orange way. Okay. This is 0.05, right? And you can look at negative Z, okay, it's 0.05, okay? So either way you work, but let's look at the positive way. Look at the Z, look at the red one, okay? Look at the red one. The red is 0.95, okay? So what we're gonna do, okay? So what we're gonna do is we just reverse what we do, right? What we do is we look at the number in the cells, okay? What is closest to 0.95 and try to check what it is, okay? And here we just keep going because it will be somewhere here, okay? Somewhere here. Let's see if I can make it bigger. Okay, this is good, okay? So what I'm going to do is look at this. 0.95 would be somewhere here, right? The middle of this two, right? Because it's 0.9495 and 0.9505 is between these two numbers. And it is between first 1, 2, 3, 4, 5, 6, right? 0, 0.1, 0.2, 0.3, 0.4, 0.5. So it's 1.64 and 1.65. So 1.6. So this is. So this guy is 1.64 and this guy is 1.65, right? Because this is 1.60, 1.61, this is 1.62, this is 1.63, right? So the middle of these two is, so that's why it's 1.645. Okay, and well, you ask if there's the middle, I just take the midpoint. That's usually you do. Okay, if there's middle, then take the midpoint, right? But for the assignment, you don't need to worry because you can just put in the number. Actually, the Excel gives you the answer immediately. Okay, but your table, you just take the midpoint. Okay. Okay. Say if you here I have 0.95, right? But if you ask like 0.951, you also give the same answer. Okay. I mean, of course, it's not quite right. You want to do interpolation, but we don't need to worry about this. Okay. For a purpose, you just take the midpoint, we're fine. Okay. You want to do it more accurate, also fine, but usually don't make a big difference. Okay. We just take any midpoint, will be okay. Which is the middle point. Okay. So now we can see this, and then we can. Is that okay for this one? Okay. And now we can look at the case of a negative value, right? So this is the positive graph. Look at the negative one. Okay, negative one. The same, but instead of 0.95, we look at 0.05. Okay, 0.05. And this will be somewhere 0.05. This will be somewhere down below 0.05. Somewhere here. Okay, here. Okay, because it's 0.05, O, and 0.0. Right? So again, this is negative 1.0, negative 1.1, negative 1.2, negative 1.63, negative 1.64, and negative 1.65, somewhere middle, so negative 1.645. Okay? So that's how you find that guy. Okay? Is that okay? So I guess it'll be same. If you want to find this bigger than 0.025, right? I do quickly because so it's asking this question. Okay, is that zeros here? More than what value is 0.025, right? And you know it must be again a positive number. The reason is because if you're negative, then it must be very big, right? So it must be somewhere here. Then this area is very small. Okay. And there are two ways to do it, right? And because this 0.025, right? So this guy must be 0.975, right? Because the error must be 1. Is that clear? Because green plus red must be 1. Okay? So look at 0.975 from that table. Okay? Okay? Let's look at the positive one. I'm not going to check the negative one again. So this table, okay? Look at 0.975. Okay? So somewhere is exactly this one. Okay? This is 1.90, 1.91, 1.92, 1.93, 1.94, 1.95, 1.96. So that is 1.96. So that's how we get our answer. Is that clear? Is that okay? So I hope you would be able to follow. For if not, that we'll be doing this again. So hopefully you would be able to know what's going on. Okay. So Now here comes the question that we'll be using, as I said, how we use it in the exam, right? So consider midterm exam, right? Follow a normal distribution with mean 20 and variance of 16. So give you the sigma is 4. Okay. So the question is, what's probability less than 16? So what we're doing here is the following: X has a mean of 20, right? Sigma is being 4. So what we're going to do is, the question is asking what's probability less than 16. So this is the area they want to know, okay? And what we are doing is we transform this to a Z here, okay? Again, a bell, okay? But now we have a mean 0, okay? Sigma is 1, okay? That's that, right? And we have to, first thing is to know what is the number here, and the same, right? How do you transform? 16 minus 20 over 4, which is -1. Okay. The transformation is minus the mean over the sigma, right? Remember how we transform, standardize. So this area less than that is same. So this is same as this one. Okay. How we do is just transform. Why this is the right transformation? Just subtract the mean over the this guy, that gives you the standard normal. So you do the same transformation on both sides of the equations. And that is something you learn in high school, right? How to operate inequality, right? You subtract 20 from both sides and then divide 4 from both sides. The inequality will remain the same, but this guy becomes standard normal. Okay, that is how in math how you do the operation, right? And less than -1 is this number, okay? And let me quickly do this. Okay, I just do the last time because it seems like you know it already. So -1. How we do that? Go to the table, okay? And we look at negative table, okay? The negative table is here. We look at the 1, okay? Let me clean this out because clear, right? Look at the 1. 1 is -1 is this guy, okay? So this is the answer, okay? We need, right? That's how you look at the -1, okay? So that's why this number, -15x7, okay? And you will do the same thing, okay? Is x is greater than 24, okay? And again, this is what you're doing, right? This is 16, this 20, now it's 24. You ask this probability, right? And this is x, right? And what you do is just again transform to z, right? This will be 0, and this is 1, right? Because you all again you are different from the mean by 1 SD, right? So this is 1. And exactly, actually, you don't need to calculate because these are the flip side, right? Less than -1 is same as bigger than +1. So this you would expect the same answer, right? Actually, you don't need to calculate because they're the same thing, right? But of course, you can do the calculation and check it out, right? Because this guy, right, is probability that z is less than 1, right? You can check the table if you want to, but otherwise that would be the answer. Okay. I mean, I checked it once, 0.8413. I can check it for you. Okay. So you will look at the positive one. Okay. Look at the 1. It's this guy. Okay. 0.8413. Okay. I check the positive set table. Okay. Is that clear? Is that clear how we do it? Is that okay? Now the last one, we want to show you is this guy, okay? Is this question, okay? Don't worry, we will be using this again as I emphasize, okay? So we're asking what is between 16 and 24, okay? So the question is this again. We're asking 16 and 24, okay? This is the area, okay? We want to know this area, but we know already the Z, okay? 16 and 24 is indeed between 1 and -1, right? So sigma is equal to 4 here, and we now have sigma equal to 1 because normal, okay? We want this area, they're the same thing, okay? And what we are going to do is we look at area less than 1, which we have found already on H413, right? And this is also coming from the previous question result, so the subtraction, right? Again, I'm not going to repeat, but this is just again kindergarten idea, right? The green one is this guy, right? And the orange one is this guy, okay? Green minus orange is the red, okay? So that is the idea what we're doing, okay? Is 70%. Actually, you don't need to calculate because this is exactly the empirical rule, right? 68% is within 1 SD, right? It's exactly what is so in the. Is that clear? Is that clear what we're doing? I mean, we'll be using it again, okay? So if you can't follow it, don't worry. I mean, you'll be there, okay? Any question? Any question? If no, don't worry. For the rest, you just can stand back and listen because there's no calculation anymore, okay? Just a bunch of facts we state, and you know what's going on, okay? So this is the last fact for normal, okay? Last fact for normal. And what is so interesting about normal is the following, okay? And we only consider for our thing is we consider independent normal, okay? So what we say is in this expression, in this first equation, what graphically is said is the following, okay? Suppose we have a bell curve for X, okay? And maybe I draw a longer one, maybe easier to see. Okay. I have a number line here. Okay. Okay. And X is this bell curve. Okay. And I have another one. Bell curve is called Y. Okay. What should we expect when we have X plus Y? Okay. And the answer is surprisingly, okay, it is still a bell curve. Oh, it should be look like this. Maybe I should just draw it in a whiteboard. Okay, here, okay. Suppose we have this line here, okay. We have an X, looks like this, okay? And I have a blue, a Y look like this, okay? And what we end up with, okay, it's like this, is X plus Y, okay? And suppose this is, we call mu X, the mean is called this is called mu Y, okay? Here we mean is mu of X plus mu of Y, okay? So still a bell, okay? The mean location, just add them up, it's just a new mean, okay? And the variance is also the same, is you just add up the variance, okay? So that's why the variance is like, that's why I draw a much fatter one, because it's having a higher variance, so it's much flatter, okay? So it's still a bell curve, okay? It's very surprising, okay? Is here we can see the bell plus bell is still a bell, okay? Before we say bell as something multiplied by something is still a bell. But here is more important, it's two bell is still a bell, okay? It is very wonderful property, right? Because you don't have this for exponential. Again, adding to exponential is not exponential, right? In general, adding to binomial is not binomial, right? You have different n, different p add together, it doesn't have to be the same. It's not binomial, right? You add different Poisson, it's not going to be Poisson, okay? Need not be, okay? And two Bell add together is still a Bell, okay? And actually go the same for the second one, okay? The second property are the same, okay? You subtract them, okay? It is still a Bell, okay? Look at the variance the same, where you do add subtract, but the mean will be different, okay? And probably ask why this is the case, because the idea is variance of x plus y, okay, is variance x plus variance y, okay? So whether you have a negative y doesn't really matter, okay? You just take out, okay? That's why you have square. And the mean is coming from the expected x plus y. It just expected x plus expected y, okay? And if y negative, then you just y negative. So basically just a and b, a and b here, and b is -1, you get the same thing. Okay, so this is the idea behind these two formula, okay? And we'll use this formula later, okay? We don't justify y because if you want to prove it, it will be advanced course, you prove it. Okay, we're not going to prove it right now, okay? So just saying, when you need to remember this, it's just say 2 Bell, still a Bell, okay? That's the thing you need to know, okay? And the mean just add up, the variance just add up, okay? If two Bell, you just add them. The mean is just mean of the 2 Bells, and variance is just sum of the 2 variance. When you subtract them, variance is still sum of the subtraction, the mean just different, okay? So the only thing you need to remember, and we don't prove it because the proof will be too involved to talk about it. Okay. Now the remaining 2 minutes, I just want to give you a very brief idea what we're going to do. Okay. Actually, just bunch of facts. Here we have chi-square. Okay. Chi is indeed coming from the idea chi is this guy. Okay. Chi-square. Actually coming from people who do typesetting. He confused chi with x. Supposed to be x squared, okay, and he just make a pick up the because in the old day the printing they pick up the stem and right and do it right, and x is actually for in those days actually they're called z squared, okay. So what is it? It's just basically we have a bell curve, standard normal z 0, okay, and we talk about z square, okay, that's chi-square, okay, z square, okay, so it looks like this, okay, that is called, that's why I have here, if z is normal, z square is chi-square, so the bell squared it become chi-square, and when you square, right, basically just like you just have here, right, put it there, right, you here, put it here, right? Because you just stack on there, right? Just stacking. Because this value, right? Square becomes somewhere here, right? Square becomes somewhere here, but you square, you just like deform a little bit, then you become this shape, okay? And finally, just give me 30 seconds. So if you have n of this chi-square add up, then it's called chi-square n, okay? How many add up together is chi-square n, okay? So not going to talk about this, but look at the graph. Just when you have only one standard normal, you just have the red one. You have 3 add up is blue, 6 add up is green. Okay, so don't worry, you don't need to remember. Just give you idea the chi-square. We will not use chi-square, but chi-square will be intermediate step. But okay, a bit rushed at the end, but we'll talk about it again next class, and we'll finish whole thing next week. So remember your homework to be due on Friday. I will see you next week. Thank you.